Thank you very much. I'll start by acknowledging my co-authors, Professor Dave Darwin, a real institution in the field of reinforced concrete and somebody I had the privilege to work with in this project. He was the motivating person who was able to convince a lot of people to put money into what we think is a very worthwhile cause. And of course, the students, James Perry and Samir Aliaso, who I advise, and we're trying to wrap up his dissertation at Kansas, who put a lot of work into the results I'm going to present. First of all, an outline of my presentation. I'm going to talk a little bit. This is an experimental program. I'll go over the motivations here in a little bit, but you may be familiar that high-strength reinforcement is a new development in the steel industry. We now have the ASTM 1035 specification, and there are higher strength bars that are creeping into the market. And when we looked at the population of test results that we had for hooks, and certainly in the case of headed bars, that issue is even worse. There's very few information that will lead us to have confidence in how we approach the design using these newer bars. So that's one of the first parts of the presentation. I'll show a little bit about our experimental study and the specimen configuration. I'm going to talk a little bit about design provisions because after all, you're practicing engineers, your concern is how does that affect my day-to-day? And we'll discuss a little bit about the main parameters that affect anchorage strength. And we will conclude with our first stab at an expression to estimate the strength of hooks with a wider range of material strengths. So the first part, as I mentioned, if you look at all these graphs that are going to present, and there are going to be a series of them, there are going to be bars in the red and there are going to be bars in the blue. The bars in the red are the data sets that were there. And the bars in the blue are the data sets that were developed through this study. So if you add these, for example, you have 30-some bars and 20-some bars, that's 50, maybe 60 hook tests. That was the entire population before this experimental program got started. Well, we start to add 80 plus 110, that's 200, so you have 240 roughly tests. That's a significant improvement in the amount of data that is available. And this is for 90-degree hooks. When we look at the problem in the context of an 80-degree hooks, the effect is even more overwhelming. We had very few, maybe a total of 10 tests. Now there's significantly larger number of tests that we have available. But it's not only a matter of having more tests that is important, is where are those tests targeted at? And so we see the breakdown here in terms of bars. We see that there have been a significant number of tests added in the range of number 11s, number 8s. And then, of course, we're looking at strengths that go all the way up. These were going to be grade 100 and grade 120 bars that can go up to well in excess of 100 KSI. And if you look at the previous range, most of the work done in number 8s and number 11s got up to maybe a maximum of 90 KSI, significantly below what this study has done. And if you look at the number 7s, we did have a little bit more of a wider range. And this one, I apologize, is just repeated. In the context of compressive strengths, that's also an important contribution of the study. If you look at the range of the tests that were done before, most compressive strengths were below 6,000 PSI, with a few maybe ranging up to 8,000 PSI. One of the stated goals of this study, and this bar here for number 11 test hasn't been updated, but all of these have gone up to we have tests ranging up to 15,000 PSI, which are included in the results that I'm going to present. So that was another one of the stated goals, to understand what happens when we use high-strength concrete. Particularly significant in the AASHTO code, because the AASHTO code will allow you to design hooks for compressive strengths up to 15,000 PSI concrete. The last parameter is the embedment length, and we see also that with the use of larger bars, increasing the population of number 11s, and also increasing the yield strengths of the steel that we're evaluating in these tests, then the range of embedment lengths went up significantly as well. Okay, so this shows a specimen configuration. It's not that different from the one that Professor Yersa used in the early studies that provided the basis for the equations in the ACI and AASHTO codes. Is a column member. It has two supports. We have a hook bar that is pulled out of the member. And all those arrows in yellow and blue that you see there is a very simple strut and tie model that is illustrating the flow of forces. As we pull on the hook, then we develop compression forces that flow towards the supports. In this case, the support's a little bit far for that strut to make it all the way out there, so it's going to need some help from the transverse reinforcement to find its way up, and then its way again to the support. And so we see in yellow essentially areas where we would expect to have tension in the specimens, and in blue areas where we would expect compression in the members. We went about designing the specimens. We wanted to have a hook failure. We didn't want the bars to yield, and so we use as a reference the expressions in the ACI code. And we started by proportioning the length of these hooks to be approximately 80% of what those would be. And by the way, those would be the same expressions that are in the AASHTO code for the development length of hooks. What we were trying to do in specimen dimensions, one of the concerns was to make sure that the struts are not too close to the location of the hook, so we don't have a confining effect from this reaction affecting what is happening over there in the area of the hook. And then, of course, we wanted to preclude shear failure, so we use ancillary reinforcement in areas like down here and over here to make sure that we were going to avoid a shear failure. So we tested several configurations of specimens. I'm going to give you a rundown of the most meaningful. The first one we did is a specimen in which there was no reinforcement within the joint region, which has always troubled me a little bit, because if you think of those struts from the previous diagram, there's a strut that goes up from the hook region, and that strut is going to cross reinforcement. But that's kind of unavoidable in the sense that we really need to avoid a shear failure in that region, and we wouldn't be able to avoid that if we leave the shear reinforcement out. But in the lower part, nonetheless, we don't have any reinforcement, and that strut will flow to the support without any help from transverse reinforcement. So that's one of the configurations that we use. In others, we use various amounts of reinforcement within the joint region. We use hooks that had a 90-degree bend, like shown, or a 180-degree bend. And then, of course, one of the aspects that we wanted to study was the effect of the placement of the hook. In a typical joint, construction-wise, folks would place the reinforcement inside of the column reinforcement. It makes more sense from the construction point of view. But there are instances in which we're going to deal with members that are not in joints. And so we also did tests where we took those bars and we placed them outside of the reinforcement, thinking that that column reinforcement and certainly the transverse reinforcement would have some confining effect that would help the strength of the hook. So we wanted to evaluate both the best case scenario and the worst case scenario. This slide shows a typical failure pattern. You start to develop cracks along the length of the bar, and then those bars tend to go towards the back of the hook. And once you get towards the back of the hook, then you see those cracks start to follow the orientation of the struts towards the two supports. And then finally, you would develop what amounts to kind of a pull-out cone. If you're familiar with an Anchorage test on an anchor, you end up pulling out a chunk of concrete. Well, that happened a lot in this experimental program. Test after test after test, you would see the hook bar come out with a much larger chunk of concrete than you would expect on an anchor. So, one of the intellectual exercises that we've done with this data set is for example, look and see how these equations compare with the equations that we use for the design for anchors. This is the same progression, but in actual images from tests. So you see how the cracking starts right at the location of the bar. We really can't see what's going on the surface of the bar, but those cracks, these are the flexural cracks. From my strut and tie model, you will recollect that this area was expected to be in tension. And so from those flexural cracks, you see those cracks start to propagate towards the back of the hook. And there is that tendency to grow towards the back of the hook, and then we start to see those cracks then evolve. Failure surface starts to look like a cone, and then finally you get pull-out of that big chunk of concrete, sometimes accompanied by side blowout in the specimen. So if you read literature on hooks, you will see people describing side blowout failures. They do happen, and they did happen in our study, but in most of those instances, it's hard for us to call it a side blowout failure by itself. It's more like a secondary type of failure. Okay, so on to the design provisions. These are the equations in the ACI code that are not significantly different from the AASHTO code. Of course, in the ACI and in the AASHTO, we're concerned about determining a development length for the hook. In our case, when we analyze these tests, we prefer to do the comparisons in terms of the stress in the bar when the failure occurred. So all we do is a simple piece of algebra where instead of Fy, we solve for that, we move it to the left-hand side of the equation. And this is the very same equation, but now it gives us an equation for stress. And this I'm going to label stress ACI is what one would calculate with the ACI equation, similar to the AASHTO equation. There's no difference in that respect. The main difference is in the square root of F prime sub C term. You're familiar with ACI design provisions. They place an upper limit of 10,000. So the largest number you're allowed to place inside that radical is 10,000. You're not allowed to take advantage of what happens between 10,000 and upwards of that. In the AASHTO code, when I read the provisions, I see that you're allowed to use strengths up to 15,000 psi, and I don't see any restriction on the square root of F prime sub C term. And that's an issue of significance in light of the results from these tests. Okay, so I'm going to go over experimental results. All the dots that you see are test results. In the horizontal axis, in this case, for example, you have concrete compressive strength. On the y-axis is the measured value of stress normalized by the equation that I just shown for ACI. So in a way, the lines are showing the degree of conservatism of the design expressions that we're using today. Okay? And you see that these lines all have the same slope. This is because these analyses and all the analyses that I'm going to show before, we used a statistical technique. It's called dummy variables analysis, in which we subtract. We assume that the slope of all these populations for different hooks are the same, and we do the regression and we determine the intercept for each one. And so the intent of doing that is to isolate the effect of the different variables, in this case, concrete compressive strength, for subpopulations of hooks. So for example, in this graph, what we're evaluating here is bar size. The blue line will correspond to bars, number 5 bars, number 6 bars for the lighter blue broken line. Then we'll go 7 and 8. 9 and number 11 bars. And so what we see from this analysis is that the test results are indicating to us that there's definitely different levels of conservatism for different bar sizes. The equation that we're using now, the provisions that we're using now, do not capture the effect of bar size appropriately. So we design for number 5 bars in a very conservative way. The level of conservatism for number 11 bars is significantly lower. What is of greatest concern is if you look at the line right there at 1, every number or line below 1 is an unconservative result. So you see that, for example, the trend lines for number 11 and number 9 bars start to get into unconservative territory at compressive strengths as low as 6,000 psi. If you get up to 15,000 psi, you're looking at measured to calculated values on the order of 80%, which is significantly unconservative. So not only do we have a mismatch on the effective bar size, we certainly have a problem with the effective compressive strength. An objective equation will show trend lines that are flat, not a slope like these ones have. This one shows, again, the effect of F prime sub c. The previous set was bigger. It didn't have any transverse reinforcement in it. In this case, I'm showing you results for joints that actually have transverse reinforcement and have, there are certain requirements within the code, and the spacing of 3-bar diameters in the hooks is kind of a dividing line. And so all of these comply with 3 dB spacing in the transverse reinforcement, so they all meet the requirements in the code, and we see that the behavior is no different. We see the same trend where we have very large degree of conservatism. You know, we're way safe with the number 5s, no problem over there. In some ways, we're over-designing the number 5s. But when we start to get into the larger bar sizes, 7s and 11s, well, here we have less confidence because we have a much lower number of data points. So you see some, you know, not so evident trends, but the larger bar sizes do tend to have significant number of tests in the unconservative regions, even when we use transverse reinforcement. This graph shows the effect of embedment length versus the bar force. That's a quantity that we like to use as a measure of Anchorage strength, is the force in the bar, not the stress. This is the actual pull-out force in the bar. And all this graph is really intending to show is that when you look at bar force versus embedment length, and we know this from splice tests and development length tests and straight bars, you tend to see sort of a linear trend. That bar force varies linearly with embedment length. In this case, maybe you see somewhat of a nonlinear relationship, but for the purpose of design provisions, maybe it is appropriate to account that as a straight line, and that would be fine. And of course, we see in this case the analysis showing that the number 11 bars, for example, the green solid lines will develop much higher bar forces than you would expect out of a number 5 bar, which is the blue in the bottom. In terms of side cover, these show, again, you know, all the comparisons that I'm going to show from now on in terms of bar force. Number 5s, we switched to green, and then we did tests with covers of 3.5 inches and 2.5 inches. In red, you see this is with heavy, so green corresponds to heavy transverse reinforcement, red corresponds to intermediate amount of transverse reinforcement, blue corresponds to light transverse reinforcement. Solid lines will tell you what the 2.5-inch side cover does. Broken lines will show what the larger cover does. And so I guess the moral of the story with these is that when we use heavy amounts of transverse reinforcement, the effective cover is negligible, is not very significant. We do see a little bit of an effective cover, is not overly significant in specimens without transverse reinforcement. So those would be the solid line in the broken line. One of the things that we looked at was the placement of the reinforcement, the transverse reinforcement in 90-degree hooks. You're allowed to place it horizontally and vertically, as shown. We did the same type of analysis for 180-degree hooks, where we placed the reinforcement horizontally and vertically. And what you see here are 4 sets of columns. Each set will correspond to different amounts of transverse reinforcement. Light transverse reinforcement doesn't meet code on the left. Very heavy transverse reinforcement on the right. And you see that the lines on the right tend to be pretty even. So again, when you put a lot of transverse reinforcement, it seems that the orientation doesn't matter. When you put a very light amount of transverse reinforcement, not meeting the 3 dB requirement in the code, then you start to see more differences. For example, in the 90-degree hooks, it becomes clear that placing the hooks in the horizontal orientation is more advantageous than placing it in the vertical orientation. Is the tendency of those bars to prevent the tail end of the hook from popping out. And in the 180-degree hooks, you tend to see somewhat of a similar effect. The 180-degree hook would come back here, and so the bars that would restrain the tail end of the hook would be the vertical bars, and you will see here that 180-degree vertical did a little bit better than 180-degree horizontal. But all in all, if you abide by this limit of 3 bar diameters, the effect of placing the hooks in one orientation or the transverse reinforcement in one orientation or the other is not significant for either orientation of the hooks. Okay, so the final part of my presentation is trying to make sense out of this and put it in the context of the design provision. So we start by a process in which we do a best fit, and this is an iterative process. So for example, this is illustrated here. The students took many attempts at trying to normalize for the effect of compressive strength, and they eventually decided that the best fit would be to normalize by compressive strength to the exponent of 0.31. It's kind of an odd number, but you know, this is an intellectual exercise. It's not a design provision that you folks are going to end up using. And you obtain a best fit line, and you obtain pretty decent coefficient of variation. Then you start to study the variations of other variables with respect to that. When you do this type of regression analysis, then you start to see the lines no longer have a slope. So here we see that we're objective with respect to compressive strength. We see that we're objective with respect to bar diameter. So all those differences have gone away. And so here what we have is a direct comparison of the two equations. On the left, we have what we have now in the Ashton ACI. On the right is what these, I hesitate to use the word predictive, but that's probably what people would call them for the most part, equations. The main difference is the effect of compressive strength and the effect of bar diameter, both of which are underemphasized in the current design provisions. All right, so to finalize, I have one slide on conclusions. Main concerns of this exercise is that we're currently overestimating the effects of compressive strength in bar diameter when we calculate Anchorage strength. This is, I think, of most concern for number 11 bars. And if you compound the fact that you are throwing in high strength reinforcement, you're putting in an immense amount of force in a bar on a very brittle failure mode, and we're having the least reliability on the bars that are most sensitive. And then, of course, we develop equations to calculate that. We found that there's no significant effect of bend angle and Anchorage strength, and there's no significant effect of transverse reinforcement and orientation on the hooks. Okay, all of this and much more information you can find in this report. I hope that information gets to you. And finally, I'd like to thank the folks that made this possible through their support. So thank you very much.